this is the first time to come to Korea, and every time I come to Korea, I somehow experience the first thing. So the first conference I attended in overseas was in Korea, and the first invitation is from Korea, and this is the first time to have talk recorded. So I'm very nervous now. But yeah, I'm talking, so thank you very much for the organizers for the invitation. So I will talk about the notion called fibered commensurability. And I don't think this notion is very popular. So actually this notion is from mapping class groups. So I will first talk about fibered commensurability for mapping class groups. And then I'll talk about the analog of fibered commensurability on outer FN. And I will try to prove that the existence of minimal elements. So the meaning of minimal will be clear in the next 15 minutes, I think. Okay. So I will talk about the mapping classes, but for the later convenience, I will use this notation. So phi is a mapping class, and S of phi means the surface on which phi is defined. So this is a mapping class. And I will define the covering relation. And actually, this is due to Calegari, Sun, and Wan. So Danny Calegari, Honbin, and Sichon Wan. So if we have two mapping classes, phi n and phi 2, then phi 1 is said to covered phi 2 if we can find a finite covering of underlying surfaces. So okay, let me denote by P from SO phi 1 to SO phi 2. So this is the finite covering. And the non-zero integer such that phi 1 is equal to the lift of some power of phi 2. So this is the definition of the covering for the mapping classes. And if we have a covering relation, then we can define commensurability. So in this way, we can actually discuss the symmetry of mapping classes. Sorry. Phi 1 is fibered commensurable with phi 2. So I will denote it by phi 1 CMS phi 2. So since we are thinking about order given by this covering relation, I will denote if phi 1 covers phi 2, then phi 1 is greater than phi 2. So if we can find third mapping class such that phi 3 covers both. So yeah, this is the natural covering commensurability. And I want to talk about basic property of this commensurability. So this is called fibered commensurability because after taking a mapping class, this can be seen somehow like the commensurability of five relations of the manifold. And this is why this is called fibered commensurability, but probably I will just say commensurability in this talk. So there are several standard facts. So Nielsen-Thurston Nielsen-Thurston type. So then I will write CMS to mean the commensurability. Type is CMS invariant. So in particular, Schilder-Nassau element is always covered by or commensurable with Schilder-Nassau element. Sorry. I forgot to mention several things, so I just want to define some more notion. So phi1 and phi2 are covering equivalent. Sorry. So each covers, so phi1 and phi2 covers each other. And from now on, let's assume that S of phi satisfies 3g minus 3 plus n is positive condition. So then the mapping class group will be very rich. And under the assumption of this covering relation is just a conjugate. So if you think about torus, then it's a bit complicated. But if we assume this, a hyperbolicity condition or things like that, then if phi1 covers phi2, then and phi2 covers phi1, then the underlying surface must be the same. So this relation is just a conjugate. But actually, to think about similar thing for LFN, we have to be careful for defining this kind of thing. So I will just want to keep that. And then, so if we have this condition, we have a classification of the mapping classes by the dynamics on the surface. And this is called Nielsen-Thurston classification. And especially, I would like to think about Schilder-Nassau. For Schilder-Nassau, for example, stable lamination and unstable lamination and we think of this as a subset. Oh, sorry. Oh, well, it's fine. Of this space, so boundary times boundary minus diagonal. And then we can think that unstable lamination, stable laminations, somehow the invariant of the commensurability. Or we can actually prove that if so phi1 and phi2 is Schilder-Nassau and they are commensurable, then the stretch factor, so logarithm of the stretch factor, are commensurable in the sense of real number. So the quotient is the rational number. This is just because we just take the powers and taking limit, taking cover or lift doesn't change the dilatation. Okay, and the main thing that I would like to think about for outer fan is an analog of the following theorem. So this is due to Calegari, Sun, and One. And they proved this for closed case. And probably I will write a little m here. So they just wrote down their proof for closed case, and I just wrote a modified version for cusped case. Cusped. So let phi be pseudo-north of element. And I will use the notation bracket phi to mean the commensurability class. So actually, so I always consider the conjugacy class or covering equivalence class. Then each commensurability class is a ordered set by the order defined by the covering. So we can think about the minimal element with respect to this order. And the theorem says that we always get a unique minimal element contains a unique and moreover, moreover, if all the singularity of the singular foliation. So here we have to think about singular foliation examination of the unstable or stable foliations are punctured. So they are on the puncture. Then, I'm very sorry. So this minimal element can be orbifold, sorry. And I will explain why we have to think about orbifold when I'm talking about outer fan analog. But we do get orbifold in general to get the minimal element. And we define somehow pseudo-north of somehow on the orbifold as a element, a mapping class that can be whose lift is pseudo-north of things like that. And so what I want to say here is that if the singularities are all on the puncture, then the minimal element is defined on the surface, so not orbifold. So not orbifold. So no singularity occurs. And the goal of this talk is to talk about the analog of this fact for outer fan.
Can you say what it means that it's not defined on orbifold?
Well, so there's no orbifold singularity on the surface. So I think surface is a part of orbifold, so this is very bad. So no singularity. So I mean orbifold, I mean that their surface with orbifold singularity. But there's no singularity for that. So for this case, is that clear? No. So to think about the minimal element, we somehow try to find the space and group acting on the space, and we divide the space by. So in this case, just we try to find the maximal group acting on the surface, and the quotient will be sometimes orbifold and sometimes surface.
So the S of T can be orbifold?
Yeah, sorry. So I was ready to say that, but yes. And so orbifold here is just a finite quotient of the surfaces. Sorry, I forgot to use this blackboard. Okay. So this is for surfaces, and so I heard that there was a course by Professor Vespino on the random work. So I would like to mention my another work is that random element is actually minimal. So if you make a random work, then the probability that you get this minimal element will converge to 1. And this actually enables you to prove that, for example, random mapping tori are asymmetric. So there's no symmetry or self-homeomorphism of that manifold, or random manifold is mapping tori and not arithmetic or things like that. So I think this is interesting thing, but it seems that so this is a joint work with Ryosuke Minoyama. And it seems to me that I and him is the only people who study fiber commensurability. So I'm feel easy to study this. Okay, so I'd like to consider the analog of this notion to OutFN. So section 1. So similarly, so I will use the same notation there, but now, so I will think about OutFN, element in the OutFN, and similarly, I will use the notation f of phi to mean the free group. So this is actually a bad notation, so this is the equivalence class, but let me just denote in this way. The free group on which phi is defined. So this is the outer automorphism. Of free group. Of rank. So the notion of commensurability can be defined for geometric outer automorphisms, but mainly I'd like to think about non-geometric case. So 2 or so rank is usually greater than or equal to 3. But if you don't know well about that, just ignore that. And I will think about this covering relation in terms of the fundamental group. So this definition is just a translate of this definition into the fundamental group. So phi 1 and phi 2 are the outer automorphism. Then phi 1 covers phi 2 if there is a embedding of f of phi 1 into the f of phi 2. So this is the embedding. And so injection, and the image of this free group is finite index subgroup. So this is finite index subgroup of f of phi 2. And we can find representatives of phi 1 and phi 2. And in the case of outer automorphism, I only think about positive powers, because in this case, positive power and negative power behave a little bit differently. Such that, so phi 2 restricted to, let me just say phi 1. So this is the image. is equal, sorry, phi2 to the power is equal to phi1. So this also means that the power of phi2 preserves the image of f of phi1. And yeah, if you know the covering theory, this is just a translation of this relation, except here, so I only consider positive power, but the translation of this relation into the fundamental group. Is that clear? So we have a covering relation, but for the case of outer automorphism of the free group, so outer Fn case, we need to slightly modify the definition of order here. So we define phi1 is greater than phi2 if we can find some positive number so that after taking power, phi1 covers phi1 to the k covers phi2 to k. So this modification is necessary basically because phi2 not necessarily preserve f of phi1. And then we can define the commensurability. So I will just write phi1 commensurable with phi2 if we can find the third mapping class, third outer automorphism, such that phi3 is greater than phi1 and phi2 is greater than, phi3 is greater than phi2. So phi3 covers both. And I'd like to think about the analog of this fact, of these facts. But before doing that, I need to remark something. So in the case of mapping class group, it is good that the Nielsen system type is preserved under taking covering. But in this case, out of Fn case, free irreducible element, which is believed to be the somehow corresponding element to Shudanasov. So somehow there are many similarity between element called free irreducible and Shudanasov. So the element of outer Fn is called reducible if it preserves the conjugacy class of free factors. And an element is called irreducible, it is not irreducible. And the element is called free irreducible, its every positive power is irreducible. Well, we can also modify the definition that every positive and negative power of your element is irreducible. So, and yeah, there are many similarities between free irreducible outer automorphisms and Shudanasov mapping classes. However, free irreducible element can be covered by reducible element. And this is because there are some elements in the out of Fn which behave really similarly as which is from mapping class group. So phi in out Fn is called geometric if we can find the mapping class on the punctured surface such that the induced action on the fundamental group not necessarily one. So okay, let's just. So if you want to have free geometric one, then we need to assume the number of puncture to be 1 is equal to phi. And so as I said now, so if you want to get free reducible geometric one, then you need to have the number of punctures is equal to 1. But if you take a coupling, then the number of punctures can increase. And after you get several punctures, then this map must preserve the conjugacy class of 3 factors corresponding to the punctures here. So that can't be irreducible. So geometric free reducible element can be covered by reducible element. So I would like to, for this reason, I would like to think about non-geometric case. And the first thing I would like to observe is that, or mention, I'm not giving proof, but the first thing we proved is that the following. So if phi is, so let's phi and phi 2 be a free, so outer automorphism. Then phi 1, and suppose they are commensurable. Then phi 1 is free irreducible and non-geometric. So non-geometric means that this is not geometric. So we cannot find any surface whose so corresponding mapping class. Geometric. If and only if, so is phi 2. So in the class free reducible and non-geometric, the property of being free reducible and non-geometric is preserved under taking coupling. So this fact corresponds to the fact here only for the Schur and Northrop case, but this is what I want to think about today. So I'd like to write an analog of the fact that I have just erased. So here, this proposition is an analog of the Nielsen-Thurston type is preserved. So especially for the Schur and Northrop case. And also, there are many interesting object that arises from free reducible outer automorphisms, and I will just list up the names. So attracting tree. So in the last talk by Professor Vestabina, and he mentioned color bottom and outer space. And on outer space, outer Fn, on outer space, outer Fn act, and the limit of the iteration of the free irreducible element is called attracting tree. So, and denoted T plus. And also, there is a corresponding object to the lamination, stable lamination. So I'm writing that things preserved undertaking commensurability. And I think of this as a subset of the boundary cross boundary minus diagonal. And also, so I'm just lazy to write in this way, but if phi1 and phi2 are commensurable and this is free irreducible and non-geometric, then log of the ratio, so we can also define the similar thing, so stretch factor for free reducible outer automorphisms, and these are also commensurable. So we can see the many similar phenomena as pseudo-north of mapping classes. And I'm just erasing here and write almost the same thing. Again, and sorry, so I also need to mention the idea of white-headed graph. So I'm sorry, I don't have time to explain the definitions. So this T plus is somehow like the stable foliation, and stable lamination is somehow like stable lamination of pseudo-Nassau. This is the stretch factor. And this ideal white-head graph, is something like the quadratic differential. So I will write in this way. The quadratic differential defined by stable and unstable foliation. And this is also, and somehow this is a lift of the quadratic differential on the universal cover. And this is also preserved somehow, undertaking covering. Oh, sorry. I erased the password. Okay, so the main theorem that I would like to think about today is the following. And I posted a paper on arXiv yesterday with the same title of this talk. So if by outer automorphism, so I have to assume several things. Outer aut is, so first I have to assume that not only non-geometric, but there's a notion called ageometric. So I'm very sorry to skip those definitions, but in the class of non-geometric elements, there's a class called ageometric. This is somehow purely non-geometric. And in the class of non-geometric outer automorphisms, there are several mapping outer automorphisms which behave similarly as geometric ones. Those called pseudo-geometric or things like that. So, and this is a complement of that. Ageometric and free reducible. So I didn't say anything, but ageometric is also preserved. Ageometric and free reducible is also preserved undertaking covering. So sorry, this is somehow like magic word for shield analysis. And also, I have to assume that the ideal for every component, the following thing. So this is in order to avoid the case of orbifold, and I'm explaining it later. But I have to assume that every component. So since this is called graph, and this is actually the graph with many components. And I want to assume that every component of the ideal whited graph is asymmetric. So asymmetric, I mean there's no graph automorphism on it. And so I think it's good to explain why we get orbifold in the case of mapping classes. So first, so let me briefly explain ideal whited graph. So as a stable or unstable relation, we get a picture like this. And orbifold actually may occur as a finite group action, so cyclic action that maps singular leaves to singular leaf. Oh, sorry. And ideal white graph is defined for on singularity, and the vertex of the ideal white graph is this singular ray, and two rays are connected by an edge if we can somehow approximate these two edges by a leaf. So in the case of surface, we always get cycle. And the reason why, in this point of view, reason why we have to consider orbifold in the case of surfaces is this graph is symmetric. So there is a symmetry that maps leaves to leaves. But in the case of outer automorphism, then the ideal white head graph can be very complicated. So this is actually defined for example, train track representative, and you pick a vertex and think about the leaf of stable lamination, which I didn't define. But and if the leaf can cover the two singular leaves, then those singular leaves are connected by a net. And so this can be very complicated, and we can assume that the component of the ideal white graph is asymmetric. And then the phenomena like this doesn't occur, so we can somehow get rid of the situation of orbifold. And actually, I think it is very interesting to get rid of this condition and think about orbifold. So corresponding object of orbifold for outer Fn or free groups. But I think this is another subject. So today I'd like to assume this condition. Then the conclusion is that, as you expect, this is a commensurability class. This contains a unique minimal element. Oh, sorry. I forgot to mention that one definition, so I'm very sorry for this. So, of course, I need to assume phi think about covering equivalence, just I did for mapping classes covering. So exactly the same definition. So each phi1 and phi2 covers each other, then they are called covering equivalent. So the minimal element here is actually the covering. More precisely, this is the covering equivalent class. So this is the statement. So any question? No? So in the remaining 20 minutes, I would like to explain how we get that minimal element. And actually, by explaining that, we can somehow explain how we get a minimal element for mapping cross groups. So the first lemma, so I always assume this. So let me call it star. So suppose phi satisfies star. Then, so this is what I call topologically minimal element. Then we can find, let me call it phi of m, whose underlying free group is minimal or maximal. I don't know how to say, but so actually there are many elements with this property. So underlying free group contains every free group of other element. So somehow we can find the maximal free group in this commensurability class, so that if we pick any element in the commensurability class, then the corresponding free group is actually a finite index subgroup of this minimal, or if in this point of view, maximal free groups. And the rank of this is the minimal. So this is a characterizing property, I think. And I'd like to explain how I get this. So if two are commensurable, then actually, so here's a tree, attracting tree, and we do not need the property of them, but what we have is actually the, so somehow quick proof. So suppose phi1 and phi2 are commensurable, so they are both are in the commensurability class. Then f of phi1 and f of phi2 act on attracting tree by asymmetry, and we can think about this group. So group generated by the union of these two groups. And in general, this group can be huge, and we cannot discuss nice property, but since we have assumed the nice property star, what we can prove is that actually this group contains both f of phi 1 and f of phi 2 as a finite index subgroup. And the corresponding idea of the mapping class group is that actually f of so somehow we get the, if we have the similar situation, then pi 1 of s of phi 1, also pi 1 of s of phi 2 act on an hyperbolic plane, so that if we assume these two are Schroeder Nassau's, then we can define the quadratic differential invariant under somehow invariant under these two actions. And if we think about this, and it's actually much easier to prove that this is a discrete subgroup, this is a Fuchsian group. How can we see that? So if there is a quadratic differential invariant under these two actions, then especially the zero of the quadratic differential must be preserved. And let's suppose that zero is inside. We can find zero inside. Then all the elements in this group also map 0 to zeros. And so if this is not discrete, we have to get the convergence sequence of zeros. But we are thinking about holomorphic quadratic differentials here. So that means that your holomorphic quadratic differential is 0 everywhere. But actually the quadratic differential we have here is not 0. So this means that this group is actually discrete. And in that way, we can prove that the desired fact for surface case. And in this case, we think similarly. So actually, by this action, we can also find the action of these groups on the ideal Whitehead graphs. And its quotient has finite number of components. This fact plus this assumption actually tells you that this group must contain these two groups as a finite index subgroup. So very similar with the reason here, but it's a bit complicated here. And we can somehow prove that this group is actually free, torsion free, acting on R3, and therefore this is a free group. So this is how the proof works. So in that way, we can somehow get the topological minimal element. And the next thing we have to think about is the dynamically minimal element. And to do that, I have to think about train track representative of free reducible outer automorphisms given by the Spina handle. So the train track representative is somehow something like a corresponding geometric object that corresponds to the surface. And I want to think about the dynamically minimal element. And to do that, I will assume this condition. So I will write down the statement now. So suppose, let's phi, and let's call it phi in some commensurability class. And I always assume stir. And suppose psi to the n covers phi, phi. So actually, this is not a side story, but this is a side story. But if this situation happens, then we can find train track representative. So here G prime. So sorry, this is not in the statement, but if this situation happens, then this is a train track representative of psi to gen, and here is the train track representative of phi with covering. So we can construct the covering of psi to gen by using train track representative of psi to gen by using the train track representative of phi. And I want to construct this. So this is the finite covering, sorry. So here's the finite covering. And since this G prime covers D, I would like to call G prime symmetric. And I also call the map G prime symmetric if this is G prime is a rift like this. So we cannot actually expect that to construct a train track representative of symmetric train track representative of psi itself in this way. But at this step, we can construct a train track representative of psi, whose underlying graph is symmetric. So what I mean is that, so this implies we can find train track representative like this. So let me just call it gamma. So, well, sorry, I just called it F. This might be, say S. So S is a train track representative of psi. And here is a train track representative of phi. And here's a rift. And after taking power, so actually I have to, so I have to say this is K. And S to the NK is a rift of T. So we can, I don't know, there might be easier proofs. And actually, in the book of Handel-Mosher, it is asked that if you have the train track representatives of some power, is it a train track representative of the original one or not? So those kind of questions asked, and I don't know how to see this, but at least we can find. So actually, I don't explain this, but to be more precise, I need to write agiometric. We can construct agiometric train track representatives whose graph is symmetric. And to do that, I actually fold the graph. So from this G prime, we can somehow carefully fold the graph so that we can define the map S here. And as a result, we can get symmetric train track representative. So sorry, I don't have enough time to explain this, but this is the idea. So just folding the graph carefully so that actually symmetrically, so with respect to this coupling, so first we get this picture and we fold G prime, but actually we fold the graph G, and then as a result we can somehow define the map F there. And the final statement is as follows. So actually from lemma 1, we see that if we pick some element in the commensurability class, then after taking power, then we actually get this situation. So, and lemma 3. So actually, I assume the conclusion here. So if we can find this picture, then we can find the equivalence class. So equivalence relation, gamma prime. Equivalence relation on gamma prime, so that the following picture obtained. No map here. So we can find the equivalence relation on gamma prime, so that here we can find the map. So we do not know if there is a map here, but we can find the equivalence relation on gamma prime, so that after getting quotient, we can get a map here. And brief idea is to define equivalence relation. So it's as follows. So x and y. So if we can find, it's called P, element in gamma, not gamma prime, and also positive, well, so this is a difficult point. So for the surface case, we can just assume that n is the integer and everything works really nicely. But in the case of outer automorphism, we have to somehow modify this definition. Yeah, so the pre-image of Z have several components, several points, and we apply estrogen to the pre-image, and if we can find some number n, so that x and y is in that image of the pre-image, then we identify those. And actually, for the case of surface, this works really nicely. And under this assumption, we can actually, for the case of surface, for example, singular point must be identified or equivalent with singular point. And also that if you pick generic point, the length here and angle here must be preserved under thinking about this relation. And that's actually the reason why we get the obifolds. So we cannot get rid of the possibility that this point will be identified this point, or things like that. But this doesn't work in this form, but we can somehow modify this idea to the case of graphs, and we can get the I can't see. Yeah, we can get this equivalence relation on gamma prime. Okay, so but if we start from the element that we get, so phi m, we get in lemma 1, and then think about lemma 2, and apply lemma 3 here, then if we have this situation, this contradicts the minimality of this, or maximality of this free group. So if we start from this group, then actually what you get is you get a map here, so you cannot get a quotient. So combining lemma 2, lemma 1, lemma 2, lemma 3, it suffices to consider the outer automorphism here, f of phi m. And every automorphism in the commensurability class defined on phi of f of phi m preserve stable lamination. And this is a situation that have already been studied by Westbieder-Fenn-Handel, that the stabilizer of this stable lamination is virtually cyclic, and we can just get the generator of the cyclic group. And the ambiguity of virtual thing is, we can get rid of that ambiguity because we are thinking when we consider the covering, we actually think this relation after taking powers. So this is how we get the dynamically minimal element. So combining this lemma 1, these three lemma, and the observation by Westbieder-Fenn-Handel, we get the minimal element. And yeah, this is a good place to stop. Thank you very much.